Hi. Thanks for the introduction. It's a pleasure to speak here. I'd like to talk about a construction of Floer homology for webs. For that, I need to explain to you what webs and forms are. But there are people, I'm not an expert on webs and forms, and my definition is not everyone have the same definition. And even for expert, I like to just set up the convention. So this is going to be the first part of the talk. So definition of, by a web, I really mean an embedded, this is going to be an embedded trivalent graph inside a three-manifold. So locally, it's either smooth or having the following singularity where three edges come together. And this singularity is a vertex, and the component of the rest is going to be called an edge. And I'd like to think about generalized cobordisms between webs, and those are two-dimensional objects embedding in the Floer space. And they will have some mild singularities, such that locally it is either smooth, so it looks like a surface, or I'll go do it over here. You will have three faces meeting at an arc, which looks like a product of interval with a trivalent point, a tripod. And there will be this one-dimensional singularity is called seams, and the complement of such are called facet. Or this is as complicated as it can possibly be. Basically, we'll have a point that locally looks like a cone over a tetrahedral graph. So have basically these 6 sheets coming together. I mean, there's one flat one, and there's one sheet coming up, and there's one meeting going from down here that meets at a single point, and that's what's known as a tetrahedral point. Okay. Yes. Great question. I should have said that. I'm not, okay. Very important remark. So edges are not oriented, first of all. And facets are not oriented. I do not, I mean that they don't have to be. I would not put orientations, and they could be non-orientable. So I've pre-drawn some examples on the slides. To answer your question, so this is a RP2 where I just glue on something like a two-handle, but you see at these two circles is forming a singularity.
And other question, for waves, do you need framing?
I don't. Well, there might be extra structure you can decorate your objects, and they might provide something like a spin-C structure. Well, they're relevant, but the definition itself would not require any of these. There's okay. Is the simplest example for webs are the theta, this embedding of theta graph, and you can take the second one is the one skeleton of a cube. There's this handcuff, glasses, or whatever, and these webs are really embedded in space, so you can have one of the edge move around a knot itself. This is yet another embedding of the theta graph, which is even more complicated. This one really comes from the following knot, which is, I guess, I pre-drew things for a reason because I will mess up on this one. Sorry. I failed my knot theory class. Okay, there you go. What you see over here is a particular quotient of it's a strongly invertible knot. I guess. So we can do the same construction for any strongly invertible knot. And let me. So how did I do that? Recall that given a knot in S3 and strongly invertible means that strongly invertible. There is an evolution if there exists a symmetry of S3 that looks like a rotation around certain axes, such evolution, orientation preserving, such that the fixed point set restricted to the knot consists of 2 points, such that sigma k is equal to 2 points. It's orientation reversing of the knot. And you can quickly examine embeddings of theta graph just by taking, I can define my web to gamma to be, first of all, this arc coming from quotienting the knot by the involution. So we got half of these. And union with the axis of the rotation, which is always an unknot. I'm just conveniently. So that's, well, that's what you get. This one over here. So one might be interested in strongly invertible knots. I guess. And also another important family of come from just the planar ones. So planar trivalent graphs. And I can generate this very easily by doing the following. Just start with a bunch of circles and just connect them by edges. I mean, many of these lies in the plane. And this is related to the colorings, and let me give you the definition. A Tate coloring is of a planar gamma is it's a 3 coloring of the edge set such that colors are distinct at each vertex. Distinct vertices. I mean, the three. It shows there should be 3 colors coming in to each vertex. And this notion of Tate coloring, it's related to this famous theorem in combinatorics, the full color theorem. It's equivalent to the following statement. Every braidless planar trivalent graph admits a Tate coloring. Yes, and this is the work of Apel and Hacking and computer. And somehow this is relevant to Floer theory because of the work of Kronheim and Morovka in this context of instanton Floer homology. The instanton for webs, and they proposed approach to the to the full color theorem. And they do this by studying the rank of certain instanton Floer homology using ISO3 gauge theory. Yeah, so part of the motivation of this work comes from constructing a monopole analog of this instanton web homology. And as it turns out, the analog is not quite straightforward, and it's not an analog. I mean, it's not quite. Maybe I was, if I am smarter. But so before, go ahead and describe what happens in monopole Floer homology. I would like to introduce another concept, definition. One set of a web gamma is two coloring of the edges of and I call the color R and C, such that if you look closely to each vertex, it should always look like 2R and 1C. For example, the theta graph can be colored with a single blue edge. And there's analogous statement there's analogous definition for forms, where instead one should color the facets. One set for usually I will denote one set as S sub sigma for form sigma it's a coloring. It's coloring of facet sigma by R and C such that sorry, I had to go back to this picture, and I need to. It suffices to require that each around a seam you have two red and one blue. In other words, if you look at the union of the red things, you should get a manifold. So over here, you can imagine the whole plane in the middle gets red, and the one above and below gets the blue. And these two coloring this type of two coloring is related to the Tate coloring by the following lemma. So if you sum over all the even one sets, meaning that each R cycle has even number of vertices, so something like that. They all has to come in pairs. This is so that you can divide the vertices into the edges into two sets, and you can put different colors accordingly. And you sum. The thing you're summing is the number of the red cycles of S, and the result is the number of Tate coloring. It is, so far, it's all combinatorics. There's no homology. And now I'm ready to state the invariant. the input the input is a web gamma and a one set S this is not a very new invariant. It's 2 years ago. It's more than anyway. We define it comes in different flavors. Each of these is a graded module over F2. These are F2 and from and bar. These W's are graded graded modules over F2, and in fact it's a graded. It's actually a module over F2 adjoint a variable where degree of this V is -1. And the structure of this is analogous to, for example, the monopole Floer homology defined by Kramer-Morovka for 3 manifolds, and which in turn is analogous to Higa-Floer homology with the plus minus infinity flavors. And given there's yet another flavor which takes the input of a web and a one set and a collection of points which I call P, which is a subset of gamma minus all the vertices. So these are points on the edges. We got a W tilde gamma PS, and this is finite dimensional always. It's finite dimensional vector space over F2. And these are supposed to be some sort of functor in terms of the cobordisms, foam cobordisms. So I will use a circle to denote one of these flavors. It's functorial. W is functorial in the sense that each foam cobordism together with a one set give rise to a map on W. let's say this is from gamma 1 S0 to gamma 0, gamma 1 S1 to gamma 0 S0, from W of the first one to the second one. And in the case in the case when sigma is closed, this construction gives you some sort of a foam evaluation, with the caveat that I have to assume some condition on the foam so that the invariant is well defined. So, for foam sigma, I'll get foam evaluation, which takes value in F2. So I'm just going to denote like this. This is basically some sort of a cyber-weighting invariant. I'm just counting. Any questions so far? Yeah.
So here the foam is inside any foam?
In the paper, I was mostly working with things embedded in S3, but in principle, you can do this for things in arbitrary four manifolds. Yeah.
What kind of equivalence do we consider like gamma P and S? Like is gamma isotopy? Is it a isotopy or orbital major? Presuming a pure one, but move P along the edges.
Oh, for this particular case. So isotopy. Yeah. Any? Yeah. Let me go on. There's some sort of module structure such that for each point, let's say P, living on the complement of the vertices gives rise to this endomorphism from W gamma to itself. It's degree minus 1. Where if I'm not writing the one set, it will be taken as a direct sum over all the one sets. Oh, should also have mentioned that these three groups are related by a non-exact sequence. I mean, as some sort of analog of a pair of spaces. So it's the homology non-exact sequence. Okay. Yeah, for this.
Can you say something about BP squared?
Oh, sorry. You need to. Yes. I have to. There's two cases. If a point, you have to look at each pieces. either the point lies on a blue edge or a red edge. On the red one, it squares to something non-zero. And this sum is a degree 2 class, which is independent of the component. Or I would just declare this to be 0 otherwise. Yes. And there's, yeah, formally it looks like something you see, for example, in instanton theory or some, maybe SL3. Hovnov-Rozansky. Okay. There's a vanishing theorem. Let me start with a picture. I realize I did not tell you what a bridge is. A bridge it's an edge for which you can find a sphere cutting your web in half, which does not intersect any other point. So it separates two chunks of the web. Or the theorem applies to a case where if there exists 3 edges colored by C that separates the rest of the web, you can prove that the homology vanishes in each case. So I'm going to write this in words. If gamma contains a bridge, then W gamma is 0. Doesn't matter what one set you use. Otherwise, if there exists, I guess, a sphere such that, let's say we're looking at the webs in S3, such that the intersect gamma at 3 points where they lies on the blue edges, then the invariant would also be trivial. This one does require input of S. There is this picture. So if you see any, there are similar vanishing theorem in instanton, and if you recall, the reformulation of the four-color theorem is that the bridgeless. It's about existence of Tate-coloring of bridgeless things. Okay. There's some properties that are harder to state. Let me just sort of give you a rough statement. So first of all, W satisfies some sort of some excision properties. In the sense that you can cut the web along some surfaces and reglue them, you will get isomorphism of the resulting web homology. In particular, this allows you to simplify some calculations or prove perhaps some relation of the webs. There's another property going back to the combinatorial lemma that I wrote, which basically relates some generators of the Floer homology to Tate colorings. For some reducible generators of some, yes. This is related to the R cycles of even one sets of gamma. This comes by observing that there are certain connections with a certain configuration of cyberbetting with zero spinors, and they would correspond to certain like coloring of the edges. Okay, so that's a summary of the environment. Yes. Not something that's easy to state, but there's one calculation I can do that comes from is sort of a consequence of the excision result, which sort of says that this invariant is like things. Imagine you have a braid that's you have a very complete braid with many components, and they connect two circles. I think this sort of configuration. Then the Floer homology is non-vanishing. Yeah. Yes. This Floer homology does not like things with less edges. Let's say this is not okay for the vanishing theorem. I guess. Yeah, like 2 is not okay either. Okay. There's nothing like for any bridgeless trivalent graph non-trivial that this rank is non-zero.
How does it look like for that example? Like give or take?
For this? All I can prove is that for some spin C structure, this one is like has rank is at least 1. Yeah, calculation for this from homology is non-trivial. I mean, I'm not exactly sure how to compute this one. This is a very this one skeleton dodecahedron is quite interesting in the monopole side because it's related to some calculation of hyperbolic 3 manifold. So, which yes.
Would you have a recursive formula allowing to compute the planar webs by reducing the faces?
Oh. there's something like, there should be some analog of like triangle relation, square relation, but I mean, I haven't, I didn't write them down. I mean, I didn't, but if you have 5 edges, you can't do any, like, you cannot reduce further if you already have this, I think.
So what's the statement about these 3 cases?
These are some examples of very simple webs.
For which the homology is.
Oh, this one is non-trivial. This is non-trivial, and this one is 0 for this particular one set, and this is a little more tricky to state. I think that's. This is a tricky one. There's no. I mean, all the relevant things are reducible. You can compute. For this story, odd and even are important. Yeah. Here. Oh. I want to say something about the gauge theory, or I'll give you some idea of what sort of the local picture that shows up when I can look at these webs and forms. Which motivates the construction. Let's see. So the main idea behind Kronheimer-Mrozka's construction is to view the webs as the web embedding in 3-manifold as some sort of orbifold, where the local model, it's like this Klein-4 symmetry, where coming from rotating around axes in R3. Klein-4. And the quotient is the familiar, a tripod. But it's more enlightening to think about the picture 1 dimension up, or in particular, if you go back to the local picture of a scene where 3 sheets meet together, you can think of this as a subset of C2, where let's say x1, x2, x3, x4. And I'll label the planes by their coordinates. So 1, 4, 1, 3. They're meeting this way. And there's a Klein-4 action acting on C2 by the following, as follows. I guess so. If you think of this as C, direct sum C. The first one comes from conjugation. The other element it's again conjugation, but where the second coordinate gets a minus sign. In particular, all these are conjugate linear. And if you like, these are anti-holomorphic. And the product of these two involutions gives you something that's actually complex linear. And if you think about, if one thinks about how to define an orbital cyberweighton, where the orbital force structure, you have an orbital force structure along the web, you will very quickly realize that you don't have enough, the structure group is a little too small. I mean, just on the connection level, you can't see, if you think about holonomy of the connection, it's not very faithful because there's only, you can't embed this Klein 4 group in U1. But I suggested by this picture, you could instead bring in conjugate linear symmetry, where you would enlarge U1 into O2, where where G mod 2 acts on U1 as generated by conjugation on S1, thinking of it as a complex number. And oops. And if you looking at the tripod again, so there should be, so one would like to prescribe some sort of holonomy of connection around each of the edge. And what that sort of suggests is that, well, we can't do that much on the connection, but there's a spinor bundle. And there's conjugate. If you put some sort of orbital chart, that this would require that as you go, you glue back the bundle, but with something conjugate linear, just like conjugating the fiber. That makes sense.
It seems that you could do a branch cover with the Klein group.
Not always. Only if the one set is even.
Can't you work with this branch cover?
Yeah, I'm about to get there. So there's an intermediate way to approach this. But before that, I just want to point out that this sort of configuration is exactly what it means to be a one set. So there's a complex and linear one, where the rest are real. This is conjugate linear. So this is the third talk of the day about real real cyberweighting. It's not, even though it's not clear from the title. So this is exactly the data over one set, which we have to impose from the very beginning. Yes, and in practice, it's not always true that one can take a client full cover of the web, but the conjugate linear symmetry is sort of providing you a double cover. So if you're given sigma s, gamma s, we consider the branch double cover, not on the whole thing, but on the real part. Consider sigma. So the branch double cover. Let's say S3. You can do this. You can do this for more general three manifold. And gammas with a superscript R, meaning that I'm taking the closure of the union of all the R edges. That's which as we notice, is a one manifold. But that's, I mean, this thing comes with the data of a deck transformation. So it's really a manifold of the evolution. But we also have to remember the C part. So that's so this should be reviewed as an orbifold with evolution. It's orbifold along something I call gamma tilde C. So that's really looking at the pre-image of the C part, and that's so one. Now it's one manifold upstairs. And so the picture to have in mind is say you have this cone angle pi along the blue part, which at some point there's this intersection with the R part. Yeah. And I need to actually do gauge theory on this. I wasn't planning on doing it because I don't have enough time. But this can be, the approach can be summarized as follows. I guess one really has to use a mix of things. The general framework, first of all, comes from Kranhammer-Morovka's Monopole Floer homology for three manifolds. But there's real cyberweighting theory that's to deal with this orbifold with evolution. So mean that you have to look at, instead of looking at all the cyberweighting solutions, you have to look at cyberweighting solutions that are invariant under symmetry, so that the thing you get at the end is gonna be an invariant of the symmetry. I mean, this starts with the work of Tian Wang, Kato, Nakamura, and this Kono, Miyazawa, Taniguchi. Yes. If you can, if it has a Klein full cover, meaning that once you take the cover along the R part, you can take a further cover on the C part, then you can, yes, you can. Z2, it's still Z2 because you're looking at invariant sets of. Oh, you need the commutes, yeah. Yes, there's sorry, there's Z2 times Z2 action on this, but one is there are really three symmetries, but there's like one is conjugately linear, and the other one is linear. So yes, yeah, and all these configurations are orbitals to remember. Like Masaki mentioned, you can also think of this as some sort of, if you take a further cover, there's some sort of complex linear symmetry in the cyber-Witten configuration space. I stick to the more general form because it can be defined for whatever webs that I work with. Wei-Min Chen, Gorge, I guess LeBrun, and many others. Yes, I should mention that to set up the gauge theory, we must specify, for example, that the cover that we work with, which amounts to choosing one set. There is something similar happening in the instanton world, similar decomposition over one sets. Not quite in the vanilla version of the SO3 homology, but you have to look at something deformed. And SU3 instanton, which is more recent. Yes, but for us, there's a, as soon as you receive this, for this one set, there's also all sorts of spin C, orbital spin C structures to consider. So the structure are quite different, and yeah, there's some annoying features of orbital spin C structure which makes the rank look rather different for examples. Yeah, so that's it. Oh. Yeah, it's I have something over there, but I think I showed you 3 evolutions, and I need to generate another one. I think the other one is maybe rotating 2-3 plane. I have it written down, but there's the local model. I mean, all of this, I mean, the consideration of even in real cyber-Witten theory, it's somehow you can write down a local model along the knot in such a way that it's manifestly conjugate linear. Yeah, you can do something like this over here. The point is that the fixed point is a single point once you do down that. So you need for that is, yeah, I guess rotation along the 2-3 plane would do the job. Yeah.
Any other questions?
Yeah.
Is there like really one J action on these also?
I think, unfortunately, oh, I thought about this once, and the conclusion back then was there won't be any J symmetry left. Yeah, taking this complex fixed point kind of kills the J symmetry. Yeah. There's a local model you can work out. I have it written down somewhere. Yeah.
Other question?
Same question. Do you know if this tetrahedron action with a singular point is invertible?
Actually, it's invertible.
You have this form with singular point.
Uh-huh.
Do you know if the action of this form, if you have this somewhere locally, if it's invertible? I think about this as a tetrahedron. It's a cone on a tetrahedron.
Yes.
Yeah. So it gives you an action, if I understand correctly, the functoriality. Or is it invertible? Is it invertible action, this guy?
Sorry, I'm not action of. I'm throughout. I'm taking fixed points, so I'm not.
Trying to parallel with things in representation theory.
Oh.
Then you have nice tetrahedron like this. That's certain property, and you could expect inversity.
Oh. Oh, I'm happy to check later.
Any other questions?
Yeah.
Can you speak louder?
So, like, you can have graphs which are not isotopic, but whose regular neighborhoods are. Is this, like, for example, like, you can take two trivalent vertices and slide them across each other? Is this invariant under, like, a loop like that, where you get different embeddings whose neighborhoods are isotopic?
Take two trivalent vertices and.
Like an example is like you have the eyeglass graph there.
Yeah.
Versus like you can take the two glasses and link them like a hot point.
Uh-huh.
Those two graphs, their regular neighborhoods are isotopic, even though the graphs themselves are not.
Oh. The graph. I'm not confused.
Maybe you're good.
Oh yeah.